Hi, I'm Gangi. I lead the inference team here at Modal, delivering frontier-level inference performance to all the customers that we work with. Today, here, I'm with Silas. He leads research at Cognition.
Yeah, so I'm Silas. I lead research at Cognition, and we build frontier coding models for our products. So we have Devin, we have like Windsurf, which is now called Devin Desktop, and we have our own series of models called SWE 1.6 is the latest one. So one of the things we did is we scaled up RL and post-training.
Huge. That's sick. So it sounds like you spend a lot of time on RL and I spend a lot of time on inference. I feel like these two fields are weirdly kind of always linked. I'm curious if you have thoughts on how inference pushes its way into things that you think about for RL.
I mean, RL has two components. There's a trainer and then there's the rollouts, and the rollouts are just inference, right? So I think the majority of an RL workload is actually just inference. So good inference, throughput, also some reasonable amount of latency is actually pretty important for RL.
That's definitely something that we see a lot across the board as trends in the industry, I would say. In terms of RL, I feel like there are a lot of different variables that you kind of have to get perfect for a successful run. If you feel like that's true, what would you say is sort of one of the hardest things to get right?
It's an interesting question. I think, honestly, RL, I think it's really just like a chain where every piece has to be correct, right? So I think there's no single hardest part, but I think that certainly first you got to get a good and stable algorithm. So we spend a lot of time tuning the algorithm, getting all the hyperparams and even a lot of the policy corrections and everything to be dialed in. I think infra is very important. Scaling to thousands of GPUs is like pretty difficult. There's both training infra, there's like the rollouts and the sandboxes and the inference engine itself. So I think a lot of pieces have to fit together.
That makes a lot of sense. I'm really curious, actually. As you work on RL, what would you say the trends are in terms of time spent working out the infrastructure kinks versus figuring out the next research idea to try and reading papers?
While research ideas are important and very key to the successful run, I think
Absolutely.
it is true that in practice, probably like 90% of the time
wow.
is just execution. I would say that includes infra and also implementing the actual like research ideas. Obviously, a lot of that is also becoming increasingly leveraged with AI. So I think we're
That makes sense.
pretty bullish on research automation. So we're using a lot of Devin for the execution, but I think that's I think an accurate characterization. Yeah.
You mentioned using AI to sort of leverage the training loop and the development loop. I'm curious, it actually affects us a lot as well. What do you see as the role of automation in the research that we're doing today?
I think it's exactly this execution part, right? I think the researcher has still the key idea, but there's just so much execution to implement an idea and see the results. So I think I actually believe that a team of 20 researchers is now worth what used to be like a team of 100 researchers, because everybody's just like running like 10 or 100 agents. There's like one example is, like there's this classic story, you like stay up until 2 a.m. to like get the training run running, then you go to bed and you wake up in the morning and it crashed an hour after you went to bed.
Yeah.
So now we have like agents monitoring training runs 24/7, jumping into triage.
Makes a lot of sense. The execution has become a lot more efficient this way. Actually, switching gears a little bit, I wanted to ask how Cognition ended up starting to use Modal in the first place.
Yeah, it's kind of a funny story. I think I've personally been a huge Modal fan for a long time. So even in my PhD student days, I've been using Modal to do a bunch of things. And yeah, I think at Cognition we use Modal for both like RL rollouts during training, but also production inference.
Interesting. In terms of the production workload, what would you say are the main factors that people should really consider when they're going out to buy inference?
Yeah, obviously everybody's talking about throughput per GPU, and I think it matters. But what we found is like a really important thing is also the utilization across the 24 hours of the day, because it's very cyclical, right? So like your daily peak might be multiple times higher than the daily low.
Yeah.
So a 10 to 20% difference on throughput GPU might be dominated by the 24/7 utilization. So I think auto scaling has become a really key factor for us.
That's really interesting. Would you say that you would prefer having an auto scaling setup for your production endpoints where possible compared to, let's say, maintaining a fixed size cluster?
I think in the end, you probably need a combination of both. But I think auto scaling, especially for bursts and launches and like daily peaks, I think is very important. And then obviously, if you have a fixed cluster, you can also find ways to have other types of workloads you can schedule into the off-peak cycles.
Makes sense. In terms of when you're buying inference, you definitely ask these questions, as you mentioned, like throughput per GPU and now also auto scaling. How about when you're designing the product for something like Cognition? How do you think about the user experience in terms of the inference speed that you must have?
I think it's a very good question. I think there's almost this like Pareto frontier of like latency versus throughput. And what we're seeing that the user demand is now actually at multiple points on this frontier, right?
I
So
see.
we have usually like a very low latency fast offering, which is for people who are willing to maybe pay a little bit extra, who like working in the loop and want the fast response. But then there's also an increasing number of people who are just very cost conscious and
Yeah.
they're willing for a background agent to wait longer and get the higher throughput.
Interesting. So there are like these two use cases, one where the user is in the loop and you want it to be as fast as possible, and a background agent where maybe you can trade off it being a little cheaper and a little slower since it's an agent running in the background.
Exactly.
In terms of these two different use cases, would you say it's then pretty important to, when you're buying inference, have the ability to choose points on that Pareto curve to serve stuff at?
I think it's true. I think you almost want a very flexible dial, so you can have your like very premium, super fast offering, even down to like maybe an offline processing offering that's super cheap and
Yeah.
very slow, and all the points in between. Yeah.
Nice. What's really interesting is my team spends a lot of time figuring out how to push that entire curve up. And we found that at different points, there are different techniques that you kind of have to use. I would say that you use really aggressive speculative decoding for the fastest real-time interactions. And then you would sort of scale that back a little bit for some balance in the middle, let's say around the 250 tokens per second throughput mark. In fact, one of the things we've been looking into is different speculation methods. So one of them that we've been training in the background for one of your older SWE models, actually, for production serving, we've been training a DFlash model, which is a diffusion model-based speculator method.
Yeah, I'm very curious to understand a little more about the speculation. So, what makes DFlash better than the previous state of the art? Let's say Eagle 3.
I would basically say it comprises of two things. One of them is that generally with the ablations that we've done, training different models with different techniques, we've made some improvements to the acceptance length, that is the number of accepted tokens each time that you draft a bunch of tokens. We've made the acceptance length a little bit higher than Eagle 3. And then the second thing that I would say is probably more dominant is the actual runtime of this draft model is significantly faster using the DFlash method. That comes down to a couple of things. One of them is the architecture of DFlash is diffusion-based. It's a single step that produces the tokens that are drafted, rather than the older techniques where those draft tokens are produced one by one over time. I would say the second part of that argument is, as we've been able to increase the accept lengths, it matters more and more that the draft stage is this constant runtime, rather than something that gets longer, the better your speculation is.
So, how much higher is the accept length in practice?
In practice, we're actually able to achieve accept lengths around 7 to 10 for workloads that are more coding dominated. I would say coding is easier to speculate on, and then comes math and then general text. But on certain workloads that are very specific to speculative decoding, for example, OCR, where you extract data from an image, we've been able to see double-digit accept length. So I think that's been a really exciting piece of progress in this area of research.
Nice. And so you mentioned that the runtime of the speculator is much faster with DFlash.
Yeah.
What does it give you?
That's a really good question, actually. So I would say that the main thing it gives you is better performance at higher concurrencies. What I mean by that is you could deploy a replica of an inference engine and just serve one user. It would be crazy fast. Like on a Kimi or DeepSeek-sized model, it would kind of be 400 to 500 tokens per second. But what about if you want to increase the efficiency there? What if you want to serve 4 times the users? Inevitably, you're going to have to do this trade-off. This is the Pareto frontier that you mentioned. You're probably going to drop in the per user experience when you have 4 times the users. Where DFlash comes in is because the drafting is so efficient, no matter how many users or how many steps that you're taking, it actually gives a better speed up at higher concurrencies compared to other draft techniques.
I think it's been interesting to see because I think traditionally our mental model was that speculation helps particularly at the like single concurrency super fast
Exactly.
setting, but I think increasingly we're also pushing speculation at higher concurrency.
Definitely.
I think one other interesting thing is how this plays into like memory bound versus compute bound. What do you think about that?
That's a great question. I would say that intuition is pretty good. So the way that I see it is, let's say we're trying to serve a really big model and you have 4 users using this inference engine concurrently. As we do a forward pass to generate 1 token each time, that forward pass on the GPU is, like you said, memory bound, in the sense that every time that happens, you have to load the entire model through the GPU. Speculation gives us the ability to actually turn this into a more compute-bound regime. So by having tokens to verify for each of the 4 users, you actually increase the amount of compute you do each time you run the model. And that actually brings you into a more favorable regime, like you said, which is more compute-bound, thus getting both better throughput and also better latency, which pushes up the curve.
Nice. What's your take on tree-based speculation?
Oh, that's a hot take. So I guess the idea about tree is you can actually have a lot more guesses and verify them all at the same time. We spent a lot of time doing research into this earlier on in the team. So around last year, we wrote a bunch of kernels to actually support this kind of tree-based verification. We found that it produces really good results when you just have one user using the engine, because you can actually get very high accept lengths. I would say it added about 1 or 2 to the accept length when you draft a tree. The problem, or I guess the reason it became less important to us, is that as we improved the technique that we had of training these draft models, the accept lengths became closer to 7, 8, 9, or 10. And that extra 1 or 2 that tree gives you wasn't as valuable. And tree itself comes with a bunch of different challenges. One of them I mentioned is you have to write new kernels and change the engine a bunch. You added a lot of complexity to actually verify a tree and then realize which branch was correct and then tell the rest of the state in the engine that. Another aspect of tree that's, I would say, challenging is in the multi-user domain, like that higher concurrency domain, you're wasting a lot of compute because you are guaranteed to have to throw away a bunch of tokens that you checked, if that makes sense.
Yeah, no, super interesting. I guess now that we're in the world of DFlash with 7 to 10 accept length, I guess we just don't need tree anymore. And also, it seems like DFlash, through its like parallel decoding model, doesn't even support tree anymore.
Yeah, I think that's actually a really good point. I would say the older methods where you produce 1 token at a time lends itself better to creating a tree that's drafted. So in a way, it is a disadvantage that DFlash, sure, you could maybe draft a bunch of different chains and verify it that way. You could see it as a disadvantage that it doesn't lend itself naturally to producing a tree pattern. But in general, I think the stars sort of aligned in the sense that it didn't make as much sense from a trade-off perspective to pursue tree any further.
So what's next for speculation after DFlash?
That's a really cool question. I guess without giving too much away, I think there is a lot more to be gained as well. In particular, I think there's a lot of work across the stack, both from the research perspective of the people working on DFlash over at UCSD. I want to give them a shout out as well. It was their idea, and we've been very lucky to collaborate with them on the project. Both on that research side and the inference engine side, you might have to add a bit of complexity. But the idea is some anchors, those are positions from which you speculate from, you have a good chance of hitting a very large length of accepted tokens. But other ones, you would basically be quite unconfident. You have to just say, oh, actually, I'm not sure about these draft tokens. And if we have the ability for speculation to tell the engine how confident it is, then we can actually save compute and be even more efficient. So concretely, this means you can potentially have speculation where you draft the tokens, but have a confidence estimate of how far you're going to get, and then only verify those tokens with the larger model, which is very expensive. I would say that's my take on the most promising next direction.
Nice, super interesting.
I was interested to get your opinion on something. I have a bit of a hot take, actually. I would say RL and inference optimization is becoming more and more similar, and there's more and more overlap over time. The reason is I watch a lot of the people that are working on research on my team, and the idea of speculation, which is to get a smaller model to do what a larger model is going to do, is a lot like distillation. And the way that we do it is you get the larger model to produce tokens, and you teach the smaller model to produce the same tokens. So in a way, it's a lot like on-policy distillation. I'm curious on if you have any thoughts around this idea.
Yeah, so I think it's actually pretty interesting. We're also seeing a much larger interest, not just at the latency versus throughput frontier, but also at the small versus big model frontier. So I think a lot of people now can actually serve maybe 50 or more % of their tokens with the smaller model and only use the large model for the hardest problems. So in some ways, the speculation is just another way of using a smaller model to just take a little bit of a lift off the larger model.
That's a really interesting way of framing it, actually. Yeah.
I think another thing I thought was interesting with your point is like, do you do any like online training of the speculator?
That's a really cool question. This is actually a direction that the field, I think, is shifting into, which is you can get a lot more efficient producing these speculators if you do it online. One aspect I'll sort of throw out here is we actually have a multi-node setup when we do the training of the speculation. A lot of the challenge behind the engineering of this training pipeline is doing a lot of data transfer between the GPUs. I think we're really lucky, actually, because our team, being at Modal, is able to use the platform infrastructure that we have at Modal. So doing these multi-node GPU training runs and so on is really easy. I actually just saw earlier this morning, one of my researchers had like multiple 8-node jobs running, and I was in a way quite happy and proud about that.
One thing that seems to be a recurring theme is like we use a lot of agents for automation. For example, like inference optimization seems to lend itself pretty well to some like auto research style self-improvement.
That's a really interesting point. Internally in our team, we actually have this thing called auto inference. We're kind of playing with the name a little bit. The idea is to have a set of configurations and you have agents go in and run experiments. Devin has been really critical for that, actually. It runs basically all the stuff that we have in there.
Yeah, and the cool thing is that then you can give Devin kind of access to Modal GPU sandboxes to iterate on the inference. Yeah, I think we've seen similar stuff for like our research automation projects. Devin actually also loves to use Modal, by the way. So there was this thing recently about the ECDSA challenge. Not sure if you heard about this, but
no, I didn't.
Google recently released this new quantum circuit that broke for the first time this ECDSA quantum algorithm. And some researchers put up a challenge for agents to compete in getting an even better circuit.
Oh, that's interesting. Okay.
And after hundreds of agents competing, agents came up with like a 40% better solution than the classified circuit from Google.
Wow.
And we obviously had Devin compete in this as well.
Okay.
And I think Devin was at the top of the leaderboard multiple times.
Nice.
And it used like Modal infrastructure to like spin up.
I think agents are really critical for research, actually for us internally as well. We're using a lot of agents to actually iterate on inference optimizations themselves. We have this internal dashboard and database called auto inference, where you actually have agents registering different serving configurations and running experiments on them through that schema. It's been really cool watching them run overnight, even without human input. Something we did actually just last week is we realized there was something wrong with one of the benchmarks, so we wanted to update it. And we got Devin to go in and find all the relevant things to run again. And it basically ran a very large experiment sweep all by itself.
Nice.
I would love to dig deeper on sort of the inference landscape that I see. I would say inference is kind of still not really solved as a problem. What would you say inference providers are kind of missing across the board?
Well, one thing that's been nice about Modal is honestly the transparency of the collaboration. It's been super nice to collaborate on behind the scenes work on like how do you do the speculation and nailing the exact benchmarks that we need.
Yeah.
I think another thing certainly is just the whole capacity domino, right? Production traffic spikes and it changes and it fluctuates and it grows faster than you think. And so having the ability to burst capacity and auto scaling has been really nice, as opposed to needing to always like play domino with like various fixed reservations.
That makes sense. Oh, should we do the interview like this?
Yeah.